Hello everyone, my name is Andres, and in this video we're going to compare the results for two identical models with different spring stiffnesses, and we'll show you how the pulse hole springs alter the different code checks performed by S Foundation. When we have a model in which there are asymmetric geometry and load distribution, as well as an asymmetric pile location, the deflections produced on the pile cap can result in a failure status for some of the structural code checks performed on the foundation. These results depend not only on the foundation's dimensions and reinforcement, but also the soil properties, which can make the pile cap prone to failing due to irregular deformations. So we have two copies of the same model over here, as you can see. Both have loads acting on the negative z direction that simulate column loads, and both of them also have some lateral loading applied. The geometry is also the same, comprised of a 500mm thick irregular pile cap, and not only that, but the piles are also the same. These are 400mm diameter piles, which are also 10 meters long, and we have a total of 16 piles arranged in 4 rows in the y direction. However, if we review the code check results for the two models over here, we will immediately notice that for the second one, we have a much higher utilization for the pad structural one-way shear code check, which in the first case barely reached 19% of the utilization with a considerably lower demand. So one other thing that might be worth mentioning is that the flexural demand for the second model is also increasing by some percentage, but if we take a look at the remaining flexible code checks, which were focusing more on the pad structural in this case, we will see that pretty much we have the same utilization in both models, which also includes the pad structural punching shear code check, which we can see has the exact same utilization. So we might be wondering what is causing this behavior. It might be worth taking a closer look at some of the other results to get to the bottom of this. So for example, here in the first model, I can go to the base shears in the spreadsheets results window, and I can do the same for the second model, and we will notice how the force values are pretty much the same for the x and z direction. We can barely see a slight discrepancy for the moment values in each direction between the two models, but this might not be very illuminating at the moment. So at this point we might be wondering, what else can we find? So why don't we go now to the strip line results for our two models. Let me just change the view over here and do the same for the second model. Going back to the first model, I can notice these values for the shear force in the XZ plane. And if I compare these to the values of the shear force for the exit plane in the second model, I can already see something going on here. We have much higher values for the second model, which is the one with the failing status. And I can also see for this first model that my shear force distribution in this plane is pretty much more even and more distributed along the X and Y axis in this case, while in the second model I can see that it is concentrating at some points. More to this, if I go now to the panel contour results, I choose displacement for the Z axis in this model, which is the one with the failing status. I can already see that we have considerable deflections in the Z plane, or in the Z direction rather, for a very large portion of the pal cap, which if we go back to our first model and we compare it to the same results for displacement in the Z direction, we will notice that these are considerably lower and more reasonable, which is why we are not getting this failing status for the pad structural check in the one-way shear code check to be more specific. And when I check this second model with the failing status, I can already notice that this pile cap is considerably less rigid than the first one. So if we have the same loading, we have the same structure itself, there must be another property that's affecting my results in such a way that is causing this failing status. So for this second model, I'll go to the define menu, click on solve profiles. I'll do the same thing for our first model, sorry. And once I get all these properties shown, let me just expand these dialogues in the second model too. I can notice that my water depth is the same. I have a one layer profile in both cases. Ultimate bearing capacity is also the same. Black fill is the same. Sol properties are the same. But if you notice the change in here, we have for our first model a much higher pile sol spring stiffnesses for the lateral friction and bearing values compared to the second model, which are barely like 2% of the values that are shown on our first model. So I can close this one so I can resume with the explanation. And in this case, the piles in our models will behave as springs, and having a much smaller spring stiffness for the second model, these springs are not providing the same stability for the current loading scenario because they are way more flexible and they allow the pile cap to suffer very high deformations. If we think of the pile cap as, for example, a cardboard panel and our fingers as the column loads in the gravity's direction in both cases, the model with higher stiffness would be sitting on the floor, for example. Meanwhile, the model with the lower stiffness would be sitting on a pillow. The latter will undoubtedly suffer greater shear forces, as we just saw, and this is due to it not being supported on stiff soil, which will also translate into a much higher one-way shear demand, which results in the failing code check for this second example. So if these pile sole springs do not provide enough stiffness to the pile cap, its higher flexibility will naturally translate into the behavior we are just observing, and with this we hope to have given a good explanation that helps clarifying how soil properties can heavily influence a foundation's demand and result in an unstable structure. Thank you for watching. For more S Foundation videos, please subscribe and check our dedicated playlists on our YouTube channel.